So now that you've had a chance to practice the basics of KSP, we're going to take a look at some other factors that actually will affect the solubility of substances. So just like the common ion has an impact on the solubility of things, these are other factors that will have effects as well. So first idea is pH. You got to remember, hopefully, from first year that H pluses, which is what creates pH. Remember that pH stands for the power of the hydrogen ion, power really talking about the exponent in the concentration. So the higher the pH is, the more OH minus you have, the lower the pH is, the more H plus you have. But you have an equilibrium that goes on in solutions of acids and bases between H pluses and OH minuses. Well, if you think about it, there's also a whole slew of ionic compounds that are hydroxides that are insoluble in water. So we can actually influence the solubility by changing the pH of the solution. If there's free hydrogen ions, free hydroxide ions floating around, we can make them go away by decreasing the pH, having more H pluses around and creating water. Well, if we take away the free hydroxide ions that are floating around, that means that more of the solid will dissociate, again, Le Chatelier's principle, to try and put back those lost OH minuses. So we can increase the solubility of a hydroxide by adding an acid to the solution because this reaction will kick in. And so this continues the idea. As a result, the lower pH will increase the solubility. Higher pH will decrease solubility. Higher pH means you have more of OH minuses around. And so more OH minuses means for any ionic substance, it's going to drive the equilibrium towards the whole molecule, towards the hydroxide molecule, as opposed to the individual ions. Another factor that will affect solubility is if complex ions are formed. So we're not talking about precipitates. We're talking about things that are still dissolved in water, but causes some ion in the solution to interact with something else and therefore leave the availability of forming the precipitate with the ionic substance. So a lot of times what's going to happen is you'll have a metallic cation that's present will actually act as an electron pair acceptor. It'll act like a Lewis acid, or it'll act like a Bronsted-Lowry base, and it'll accept an electron pair. It'll accept something with a pair of electrons. As a result, these cations may complex with certain anions and create what's referred to as a complex ion. So don't worry too much about the Lewis acids and base stuff. AP doesn't even go into it. But I know that some of you learned the definitions of Lewis acids and bases. In any case, we'll get to an example in a moment. In any case, what happens is you get an equilibrium of formation of that complex ion. So KF, F stands for formation. If you have that complex forming, that's a secondary equilibrium reaction that's happening, and it's drawing the ions away from that original solubility reaction that we're looking at. So if KF is reasonably large, that means more of that insoluble or that ionic substance will actually dissolve. The complex ions are going to remove the cation from solution, and so it's going to shift the equilibrium to the right. So here's an example that you can actually see. So you have zinc hydroxide with a solubility of 3.0 times 10 to the negative 16, or solubility product. So KSP, 3.0 times 10 to the negative 16. You also have a KF for the formation of a hydroxo complex of zinc OH minus 2 minus. So here's the complex ion. It's soluble in water. This is a solid, but this is aqueous. Its formation is 4.6 times 10 to the 17. So that's a pretty high formation. That means it supports the formation of this guy very strongly because this is your product. Okay, big number favors the products. Little number favors the reactant. So this equation is favoring the solid, but this equation is favoring that complex ion. So what happens is when you put the zinc hydroxide in solution, you wind up with hydroxide ions recomplexing with the zinc hydroxide to give you these these like super hydroxide, I can't think of a word here, super hydroxated, it's not even a word, zinc ions. And so we are actually going to treat this as though it were a Hess's law kind of problem. We can take the two reactions, add them together to show what will really happen. Zinc hydroxide will complex with more excess hydroxide ions and create this complex ion. So we add the two equations together, but if you remember in Hess's law, I guess we did add delta H's. In this case, we're multiplying the KSPs. So to get the constant of the overall formation of this ion from the solid, we're going to multiply the KSP and the KF in order to get a value. So then if you have a situation such as this, where the constant is 1.4 times 10 to the 2, like we saw, this guy's aqueous, this guy's aqueous, this guy's solid, so the equilibrium expression is just the complex ion divided by the hydroxide ion concentration. We can solve for the question of how much hydroxide is needed in order to get all of the zinc hydroxide to dissolve. So you can see here we've got the equation set up. All we need to do is rearrange and get to the amount of zinc hydroxide, or the amount of hydroxide that you need in order to get it all to dissolve. So we need to add enough OH minus ions to get all of this to complex with the OH minus ions to give us this guy. So all of this, so where is this number coming from? All of this, 0.015 moles, has to be converted into this. So how much hydroxide do we need to get that 0.015 moles of zinc hydroxide 2 minus formed? That's what this calculation is letting us see. So that's the idea of complex ions. So it's kind of like a Hess's law problem. But remember that for the constants, you're actually multiplying them together. You're not just adding delta H's, you're multiplying the constants together. A third idea that affects solubility is amphoterism. So you've got insoluble oxides and hydroxides that can be made to dissolve more easily in acidic or basic solutions. So we've already talked about the fact that you can get hydroxides to dissolve in acidic solutions. You can get oxides to dissolve in acidic solutions as well. So if you have the solution basic, that means less of the solid is going to dissolve. So it's going to drive it one way or the other depending upon not just a little more to do it with it than pH. We'll expand on the idea in the acid-base unit, but basically increasing the concentration of this will get more of this to dissolve. Increasing the concentration of a base will get less of these guys to dissolve. That's the basic idea there. Okay, we're going to quit here. The last idea is qualitative analysis, precipitation and separation of ions. So we'll get into that in the next video because it's kind of a different topic.